Hello everyone, welcome to Helm of Science. So in the last class, we have discussed the introduction to the set theory, that is the introduction to the sets, that is what is set. Okay, so what is the representation of a set, that is roster form, tabular form, and we have discussed some important sets. Okay, so today we will start our class with the topic of types of sets. Okay, so we will start with the topic of types of sets. Types of sets. Okay. So the first set that we will talk about, the first type, that is the empty set, or it is called null set. Okay. Empty set or null set. It is actually what? It is the set containing zero number of elements. Set containing zero number of elements. That is, it is not having any elements. Okay, inside it. Now this is denoted by this empty set or null set is denoted by phi. Okay, this phi is the representation. We write this one as, that is the, we write this null set as phi, and we write it in this. That is, it is containing no elements. So in the second bracket, no element is present. Okay, so this is phi. Phi. Okay, so this is the set. Here you have to note one thing, that many students do this wrong. That is, when we have, they found that when we have an element 0 inside the set, that is the square bracket, or it is actually the second bracket. So whenever they see that whenever if there is present 0 inside the set, they call it as phi. But this is wrong. It is not a null set, because here a element is present, that is 0 inside the set. So the condition for the null set, that it is having no elements, that is, it is containing zero number of elements. Okay, that is, it is containing zero number of elements, but not 0. This is the mistake here. Okay, many students think that this is phi, but this is wrong. The actual process, that is this one. This is called phi. Okay, and since I have told that the set containing zero number of elements, that is number of elements, that is the cardinal number we have discussed in the last class, that is cardinal number of a set. So cardinal number for this null set is equal to 0. This is 0, but this thing is wrong. Okay, so cardinal number of the null set is 0. Okay, so this is correct. This is correct. Okay, it is actually what? It is the number of elements. Number of elements in the set is 5, and 5 containing zero number of elements. Okay, now we can take an example of this 5. Suppose example, we have taken a set, suppose capital X is equal to, we are representing in a set builder form. Suppose here X such that this X square plus 1 is equal to 0, and X belongs to R. So we have to write the values of X which satisfy this equation, and we have to form a set of that. That is, we have to form this set X, capital X, such that this X is satisfying this equation, and X is belonging to real number. Okay, so if you see this carefully, this equation, now you can see that X square, whatever the value of X square will be, it will be greater than equal to 0. Okay, greater than equal to 0. Now here if we take X equal to 0, so it will be 0 plus 1, that will be 1. But except 0, if any value, any real value we take, it will be greater than 1. Why? Because it is X square plus 1, and it is given that X square plus 1 will be equal to 0. So this is not possible. Not possible. possible. Why not possible? Because we know that x square is greater than equal to 0. If we put a 0 in place of x, it will be 0. Other than 0, any number that we will choose, it will be greater than 0. Okay, because it is squared. So if we take negative number also, it will become as square. That means it is becoming positive number. So it is greater than 0. Okay, so that means x square is greater than equal to 0. That means x square plus 1 will be 1. We will add 1 in the equality throughout, so it will be 1. So x square plus 1 will be greater than equal to 1. So this equation is not satisfied. That means this equation cannot be true. Why? Because x square plus 1 is greater than equal to 1. So it will not become 0 in any case. Okay. So here we say that here no value of x is present such that this equation will satisfy. So we take that capital X is containing no x, or we take zero number of elements. That is, no element is present. Okay. So no element is present means it is x is belonging to, that means x is having zero number of elements. That is, we take that this is 5. That is, x is a null set. Okay. Since it is containing zero number. This is the example. Okay. Now we come to the next top. That is the next type. This is the finite set. Finite set. Now write it down. What is this? The set having finite number of elements are called finite okay, we have to write it in the roster form. Okay, so let's say x such that x square minus 5x plus 6 equal to 0. Okay, and x belongs to 0. Now you can see here that we have to find the values of x for which this equation has to be satisfied, and x to real number. Okay, so let us solve this. So this is actually what, x square minus 5x plus 6 equal to 0. This equation will be satisfied by the values of x, and these values we have to represent in the roster form in the set capital X. So if we solve this one, this will be x square minus 3, its middle term factorization, plus 6 equal to 0. Okay, so this will be what, x into x minus 3 minus 2 into x minus 3 is equal to 0. That is, x minus 3 into x minus 2 is equal to 0. So from this we get that either x equal to 3 or x equal to 2. So here we have got two values of x which will satisfy this equation, that is x square minus 5x plus 6 equal to 0. Okay. So here we write that the x, that means the set capital X, is containing two elements, that is 2 and 3. Why? Because the values of x that we will satisfy this condition, x square minus 5x plus 6 equal to 0, among all the real numbers, it is 2 and 3. Only 2 and 3. Nothing will this satisfy this equation except this 2 and 3, because we have got two values. Okay, by satisfying this equation. So this is x equal to 2 and 3. Elements present is 2 and 3. So you can see that here number of elements in this set x, that is cardinal number of x, is 2. So you can see that these elements can be countable. That means we can say that that means the number of elements present inside this set is 2. So it is countable. That means it is the finite set. Okay. So this is the example. That is, x is having the elements 2 and 3 only. That means it can be countable. We can say that two elements are present inside the set and the cardinal number is 2. So we can say that this is a finite set. Finite set. Okay. So I think you have understood. Now we come to the next type, just opposite to this, that is the infinite set. So it is very simple. You can very well understand that the set containing infinite number of elements. I'm writing the set having infinite number of elements. Okay, that is the set is having infinite number of elements, that it is uncountable. Okay, we cannot count the number of elements and we cannot say that how many elements are present inside this set. So the examples for this we have done in the last class, that is we have done the set of natural numbers. What is the set of natural numbers? It starts from 1, 2, 3, 4 and up to infinity. Okay, it is up to infinity. We cannot tell that how many natural numbers are there in this set. There are infinite natural numbers. Okay, we cannot count the numbers. That is, we cannot tell that how many animals are present in the set of natural numbers. So this is an example of infinite. Okay, it is an infinite. That means the natural number, the set of natural numbers is an infinite. Okay. Again, the set we have done, that is the set of whole numbers, the set of rational numbers, the set of real numbers. These all are under the infinite because it has infinite number of elements. We cannot say that how many elements are present inside. Okay. Now, another example we can take, these students just do not just look into it properly, so they just do the mistakes. That is the, suppose I have taken a set, suppose A, capital A, it is X, X is, that is greater than equal to 2 and less than 4, and X is belonging to real number. So we have to tell this how many elements are present inside this set. Okay. Now, students, what they do is they just write it that here it is present that A is a set where X is a value such that the values of X is greater than equal to 2 and less than 4, and X is a real number. So they write that it is greater than equal to 2. So here 2 and 3 will be the answer. Since it is X is greater than equal to 2 and less than 4, so two numbers are satisfying, that is 2 since it is greater than equal to, and it is since less than 4, so only 3 will be the answer. This is this is totally wrong. Why? Because here it is present that X is belonging, that is here X is greater than equal to 2 and less than 4, but another condition is given here that X is belonging to real numbers. So we, if you see carefully, in between 2 and 4 there are infinite number of real numbers present, not only 2 and 3. Okay, if it were said that X is belonging to natural number, then we have written that 2 and 3, but it is given that X is belonging to real numbers. So all real numbers means what? 2.1, 2.2, 2.12, 2.23, an infinite number of elements. So in between 2 and 4, if it is real number, X is a real number, then it is infinite number of elements present inside the set in between 2 and 4, not only 2 and 3. Okay. So students do these mistakes. So they have to be very careful about this. That is, here X is belonging to real numbers. So we cannot write only 2 and 3. Okay. Then this will be wrong. So here, what is the answer? That is, A is an infinite set. Why? I have just explained that since X is a real number, so real numbers means what? All the numbers that is present. That is, we used to think that In between 1 and 3, only one element is present or one number is present, that is 2. But this is not, it is wrong concept. In between 1 and 3, infinite number of elements. In between 1 and 2, infinite number of numbers are present, real numbers. 2 point, in between 2 and 4, 2.3, 2.5, 2.6, 3.12, 3.112. They're infinite. Okay, we cannot count them. So A is an example of infinite set. Okay, now we come to the next type, that is the singleton set. Singleton set. So what is the singleton set? Write it down. The set having only one element is called a singleton set. Okay. So in the null set, we have seen that if a set is containing zero number of elements, then it is called a null set. Now here what it is telling? It is telling that a set which will have one element only, one, that is the number of elements present inside the set is only one, then we will call that set as a singleton set. Okay, singleton set. So you can very well understand from the word also, that is, it is singleton set. Single, that means one. Okay, so the set having one element only is called a singleton set. Suppose example, that is, you can write here also that singleton set means number of elements present inside a set is one. That is, I am writing this one, that suppose here it is mentioned, suppose an example is taken, that is an set, a set capital B, and here it is x such that the values of x will satisfy this equation, this condition, that property will give it, and here it is given a condition that x is greater than -3. Okay. So we have to find the values of x which we will satisfy this equation x square plus 5x plus 6, and also the condition is given that x should be greater than -3. Okay, so let us solve this. That was what values of x will satisfy this equation, x square plus 5x plus 6 equal to 0. Okay, so here it will satisfy, that is x square plus 3x plus 2x plus 6 equal to 0. So it will be what? It will be x into x plus 3 plus 2 into x plus 3 is equal to 0. That is, you can write x plus 3 into x plus 2 is equal to 0. So what values of x we will get? It is either x equal to -3 or x equal to -2. So the values of x that will satisfy this equation is -3 and -2. But very important thing, that here it is given a condition that x should not be equal to -, it will be greater than -3. So we know that -2 is obviously greater than -3. So here the set B we will have, the set B will have only one element of x, that is only one value of x that will satisfy. Actually the value of x satisfying this equation is 2, that is -3 and -2. But here it is given a condition that x cannot be equal to -3, it is greater than -3. So we have to take only the value -2, not -3. We cannot take the value -3. Okay. So here the element B will have only one element, that is 2. So this B is called a singleton set. Okay. I think you have understood that what is singleton set. That is, the B is having only one element inside the set. Okay. So here cardinal number of B is what? For singleton set, cardinal number of any set. If this set, if that set is singleton set, so cardinal number of that set will always be 1. Okay. So here the cardinal number of set B is only 1. Okay. That means B is a singleton set. Okay. If anywhere it is written that cardinal number of any set, cardinal number of any set is equal to 1, then without fail we write that that set, the set which will have, suppose A, B, X, whatever the set will be, is a singleton set. Singleton set. Okay. Now, now we come to the next topic. That is the next topic. Next type. That is the equivalent sets. Equivalent sets. Okay. So what is this equivalent sets? Write it down. Two sets having equal number of elements are called equivalent sets. That is, if we have a set, suppose A and B. So for the set A and B to be equivalent, it is telling that number of elements in the set A should be equal to number of elements in set B. That is, kernel number of A and kernel number of B will be same. So this is the condition. Okay. That means whenever we have that kernel number of any set is equal to kernel number of any another set, so then we will say that that two sets are equivalent sets. Okay. So if I take an example, suppose I take a set A, inside it 1 and 2 are present. That means the element is 1 and another B is element that is A and B. Now here it is not necessary that this 1 and A should be same. Okay. So then it will be another condition. Then we will do in the next part, that is after this equivalent. So here it is not given that the elements should have to be same. It is telling that number of elements present, so the in the set will be same. So then it will be equal sets. We will do in the next topic. That is the next part, the next type we will have. Okay. So here it is telling that number of elements. You can see that number of elements in set B is also 2. Here it is 1, 2, and it is AB. Here A is not equal to 1, 2 is not equal to B. Nothing this case. Okay. So here it is telling that only number of elements, that is n of A, is equal to 2, and here a n of B is also equal to 2. So we can say that A and B are equivalent sets. Okay, A and B are equivalent sets. Why? Because we have just discussed that number of elements in set A and number of elements in set B is equal to 2. Okay, no matter that what the elements are. Okay, elements can be different. So the main important thing is that number of elements should be same. If set A has, if two sets are equivalent, then they must have the number of elements same. That is, if A is containing 3 number of elements, B will also have 3. If A is containing 7 number of elements, B will also have 7. Okay, that is the condition of equivalent sets. Okay. Now we come to the next type that we are studying. It is equal sets. Equal sets. Okay. So here the condition applied that two sets having same number of elements, and also elements are equal, then the two sets are called equal sets. Okay. So what it is telling, the two sets having same number of elements and also elements are equal. This condition is applied here. So in the equivalent set, it is only given that two sets having same number of elements. Up to this, it is equivalent. But if it is given that the elements should have to be equal, that means if elements are also equal, then we will call that it is equal sets. That is, suppose I am taking an example. Suppose a set A is containing x such that the values of x will satisfy this equation. X is belong to real number. And another set B is given where x is a prime number less than 5. So these two sets are given. So so we have to tell that what type of sets are they. Okay. So if you see carefully, if we write this set A in roster form, so how we can write that it is actually what the values of x will satisfy this equation, that is x square plus 5x plus 6 equal to 0. So here the factorization will be x minus 2 into x minus 3 equal to 0. So the values of x that will satisfy x equal to 2 and 3. Okay. So the values of x will satisfy. So here A is containing only elements 2 and 3. Therefore, we will write say as roster form is 2 and 3. Okay. And in the set B, it is given that B, that is B is a set where the values of x will satisfy such that x is a prime number less than 5. So less than 5, the prime numbers are only 2, 2 is a prime number, and 3, 3 is a prime number. 1 is not a prime number. So except 1 and 4, the elements 2 and 3 less than 5, that is the first numbers less than 5, the elements from 1, that is from x equal 1 to x equal to 5, the prime numbers are 2 and 3 only. Okay. So here it is telling x is a prime number less than 5, that is only 2 and 3. So here B is what? B is containing two elements in the set. It is 2 and 3. So you can carefully see that A and B, the sets are all are exactly identical, exactly same. Why? Because the number of elements in set A is also 2 and number of elements in set B is also 2. Okay. If the A element, suppose it will have 2 comma 3 and suppose B is having 5 comma 6, then we will say that these two sets are equivalent. Okay, because here number of elements in these two sets are same, but the elements are not same. Here you have to see that here A is having the element 2 and 3, B is also having the element 2 and 3. Okay, so number of elements in the set is also same and the elements are also same. Elements are also matching with them. Okay, A is also having 2 and 3, B is also having 2 and 3. So by combining these two cases, we can say that A and B are equal sets. Okay, so they are satisfying the condition of equal sets. That is, the elements are also same and the number of elements are also same. Okay, now we come to the next. Now here, important thing that we have to know the first thing, all equivalent sets are not equal. And then second point is all equal sets, that is here the first notice, that is the first important thing, that is all equivalent sets are not equal sets, and the next all equal sets are equivalent sets. Why? Please understand this. See, in equivalent sets, what we have, only the number of elements should be same. Okay, no matter that elements are same or not, elements can be different. So why this is what it is telling, that if a set A is having it is equivalent. It does not mean that it is equal set. That means if two sets are equivalent, it does not mean that they are equal sets. Okay. Why? Because they may have different elements. That is, if they have same elements, that is no problem. That then we will call it as equal sets also, and equivalent obviously. And but if two sets are equivalent, we cannot directly say that they are two equal sets. Okay. So because in equivalent sets, only the number of elements will be same. Elements can differ, can be different. Okay, may differ. But in equal sets have the condition that number of elements should have to be same and the number of elements is also same. That is, number of elements is same and the elements are also same. So in equal sets, the condition of two sets to be equivalent is also satisfied. Okay, it is also just satisfying satisfying the condition of the equivalent sets. So if two sets are equal, then we can directly say that that two sets are also equivalent, because in that the elements are also same. If the sets are equal, the elements within them are also same and the number of elements is also same. Okay. So if two sets are equal, then we can directly say that two sets are equivalent. But if two sets are equivalent, we cannot directly say that they are equal sets. Okay. So I think you've understood. Now the next part, that is, now we have finished this types of set, that is equal sets, equivalent, singleton, infinite, finite. Okay. Now we are talking about a very important thing of set, that is the subset. What is subset? Okay. So what is subset? Suppose if set, so I'm taking the if set A is a subset of set B, then all the elements of set A lies in set B. Okay, so what it is telling, that subset it was subset is if a set, suppose A is a subset of set B, then all the elements of set A will lie in set B. That means, suppose I am taking an example. Now subset is denoted by this symbol, that is, we have just written B in vertical, that is horizontal. Okay, this is the symbol of subset. Okay, now I'm taking an example. Suppose a set A is having 1 and 2, that is the elements 1 and 2, and set B is having 1, 2, 3, 4. Now what is the condition here? Here, if set A is a subset of set B, then all the elements of set A will lie in set B. You can see here that set A is having 1 comma 2, that is 1 and 2 are the elements of set A, and B is having 1, 2, 3, 4. So automatically the all the elements that A is having are present inside the set B also. So the elements, all the elements, that's the whatever the elements are present inside A, all the elements are present inside 2. Here only 2 elements are present inside this set A, but these both 2 elements are also present in set B. So all the elements of set A is present in the set B. So here we will say that here A is a subset of B. Okay. So this is the concept of subset. That is, if a set A is a subset of set B, so all the elements of set will lie inside the set B. So for an example, we have taken this one. That is, if A is having 1 comma 2 and B is having 1, 2, 3, 4. So here 1 and 2 both are present in B. So all the elements of set A is present in set B. So we have taken that A is a subset of B. Okay. Now example, A is a set, suppose 1 comma 2. Okay. So what are the subsets? Suppose what are the subsets possible? So A is having one and two elements. Okay. So what are the subsets of this set? Suppose I'm taking that a set where only one element is present, that is one. Okay. So all obviously here the element one is present inside this set A. So obviously all the elements, that is one element also present here. So the element of this set X is present inside this. So we will say that X is a subset of A. X is a subset of A. Okay. Again, if I say capital Y, suppose it is containing element 2. So 2 is also present inside the set A. That means all the elements that Y is having, it is present inside A. So also Y is a subset of A. Again, if I take B set, suppose it is containing 1 comma 2. Okay. So here also all the elements 1 2 also is present inside A. So all the elements of B is also present in A. So obviously B will be a subset of A. Okay. So and another set is present, that is, if I say suppose phi, phi means null set. Now here nothing is present. So you can very well see that besides 1 and 2, it is having no elements. Okay, no element is present. So it is also present inside the set because except 1 and 2, nothing is mentioned. So we can say that phi is also a subset of 2. You have to remember a point that I will write it down in the next topic, that is next part, that phi is a subset of every set. Okay, phi, that is null set, is a subset of every set because it is what here A is 1 comma 2 and phi is what, it is having no elements. So it is also all the elements of, that means it is having no elements, so it is also present inside this set A, but we are not writing this one, we are writing only 1 and 2. Okay, so besides 1 and 2 nothing is present, so that nothing is actually phi set. Okay, so phi is also a subset of this set A. Okay, so the subsets of this, the subsets are, there's 1, there's 2, there's 1 2, and another is phi. Okay, so these are the subsets. Now we have to know that I was telling that phi is a subset of every set. Okay, and another, every set is a subset of itself. Why? Because you have seen here. Here A was 1 comma 2. Also we have taken 1 comma 2 as a subset of this one. So this is actually what, this is the set itself. So it is also a subset of this set. Why? Because all the elements, if we take another set having 1 comma 2, so all the elements that's in that set is actually this 1 and 2. So here we can say that all the elements of this set is present inside A. So also 1 comma 2 is a subset of 1 comma 2. That is, every element, every set is an subset of itself. Okay, so I think you have understood. Now another example I'm giving, that is, suppose a set A having 1 2 3. You have to write the subsets. Write the subsets. Okay. So what will be the subsets? Subsets will be, suppose if I take a set A having only 1, so this will be a subset. Then 2, then 3. Then we will take 1 comma 2 also. Then 1 comma 3 also. Then 2 comma 3 also. And also the element itself. Sorry, the set itself. That is 1 comma 2 comma 3. and we will have 1 comma 2 1 comma 3 1 comma 3 2 comma 3, and another we have just have told that 5 is a subset of every set, so 5 will be another set. So 1 2 3 4 5 6 7 8. Okay, so these will be the subsets. Okay, why? Because if we take different 8 sets, suppose like G, so all these sets are the subsets of this one, because all the elements of this set, that means if this considered a set, this one, so all the elements of these sets are present inside this one, A. Okay, so these are the subsets. Okay, so here another very important thing, that is most important formula we can tell, that number of subsets of any set, what will be that? See here, in the next, or you can say in the previous part, here we have taken A as 1 comma 2. So here cardinal number of A is what? 1 and 2, that is here the two elements are present, so cardinal number is 2. And we have got the subset as 1 2 3 4, that is we have got 4 number of subsets, that is the number of subset is 4. Okay, and in the next case where we have just taken the example that A is containing 1 comma 2 comma 3, so in this case the subsets are 1 2 3 4 5 6 7 8. So here the element present inside this set is 3, that is cardinal number of set is 3, and here it is given that the number of subset is 1 2 3 4 5 6 7 8. So 8 subsets are present. So from this we can easily say that in the previous part we have seen that number of elements is 2, the number of subsets is 4. So number of subsets we can write it as is equal to 2 square, we can write. Okay, number of subsets, we can write here number of subsets is equal to 2 square, that is equal to 4. And here in the next example we have taken the number of elements as 3, that is the number of elements present inside the set A. So here we have got number of subset is 8, that is 2 cube. So you can very well understand that whatever the cardinal number we are taking, that is whatever the cardinal number present inside this set, that is, it is becoming the power of 2. That is here cardinal number of A was 2, so it has become 2 to the power 2. In this case, the cardinal number of 3 is, that is cardinal number of set A is 3. So the number of subsets we have got 2 to the power 3. That means whatever the cardinal number we are taking, it is just rising to the power of 2. So we can very well understand that from this an important formula, that is we can write important formula, that is number of subsets of any set, suppose the set is A, it will be equal to 2 to the power cardinal number of that set, that is number of elements present inside the set. In set, here we have taken set A, so here it will be 2 to the power cardinal number of A, that is 2 to the power of n. Okay, so this is a very important formula, that number of subsets of any set A is 2 to the power na, that is 2 to the power the number of elements present inside the set A. Okay, so I think you have understood. Now we will talk about the next part, that is the proper subset. Proper subset. Okay, so what is proper subset? That is all the subsets excluding itself. That is, in subsets, what was happening? In subsets, we were taking the element, that is the set itself as a subset. That is, in the first example, and in the next example, we are taking here, we have just taken the set A as 1 comma 2 comma 3, and we are taking 1 comma 2 comma 3, that the set itself as a subset of this. So it is the case of subset. But in proper subset, what it is telling that if we have a set, suppose A 1 comma 2. So here the subsets are what? Subsets are 1, this one, 2, 1 comma 2, and another we have 5. So in the subset case, this is the subsets. But in proper subset, it is telling all the subsets will be present, excluding itself. That means excluding the set itself. That is, we cannot take this 1 comma 2 in the proper subset. Okay. So if I just write that A is a subset, that is A is a set, is 1 comma 2. So if I have to just write that what are the proper subsets of this set? Fine. But we will not take this total set that is given, that we have taken, that A is equal to 1 comma 2. Then we cannot take in case of proper subset. Okay. So 1 comma 2 is not present. So the proper subsets will be this one. Okay. Also in the next case where we have taken A equal to 1 comma 2 comma 3. So in that case also proper subsets will be proper subsets will be 1, 2, 3, then we have 1 comma 2, then 1 comma 3, then 2 comma 3, and 5. But we will not take 1 comma 2 comma 3 because it is not satisfying the condition of proper subset. Proper subset is telling that all the subsets will be there excluding the itself. Okay. So proper subsets is this 1, 2, 3, 4, 5, 6, 7. Okay. So if someone tells you that what are the number of proper subsets, number of proper subsets of any set, see here in this set we have written all the subsets, but we have not written this one element set, that is 1 comma 2. So in case of proper subsets, what will be the number of proper subsets? It will be number of subsets that are present minus 1. Why this minus 1? I am writing this one. This will be 2 to the power number of elements in that set minus 1. Now you can see these are the what? These are the number of subsets. We have just written that number of subsets is 2 to the power na, that is 2 to the power cardinal number of the set. So this is also number of subsets minus 1. Why this minus 1? Here it is minus 1 because we are excluding the set itself. Okay, that is why the number of proper subsets of any set is 2 to the power na minus 1, to the power of cardinal number of any set to the power minus 1. Why this minus 1? Because in the proper subset we are excluding the set itself, but in subset we used to calculate the set itself. Okay, so in the formula of number of subsets we are writing 2 to the power of cardinal number of any set, but in case of number of proper subsets we are writing that number of subsets we are taking and we are excluding the this set itself, that is number of subsets minus 1, that is equal to the power of na minus 1. You can see here also that in this case here we have taken this one, this example. Here if we just apply this one, number of proper subset number of proper subset will be equal to, here the number of subsets was what, 2 to the power of 3 minus 1. Here minus 1, why? Because we have excluded the term 1 comma 2, sorry, 1 comma 2 comma 3 here. So it will be 8 minus 1, that is 7. You can verify as well. 1, 2, 3, 4, 5, 6, and 7. Okay, and in that case, in this case, number of subsets will be 2 to the power of 2 minus 1, that is 3. You can check 1, 2, 3. Okay, so this is the formula of number of proper subsets. And very important thing, proper subset is denoted by proper subset. It is denoted by this one. We write this U and then we put a dash like this. Okay, so if suppose this one like this, that this means that A is a proper subset of B. Okay, now things to remember, suppose very important things that we have to remember about this subset and proper set. That is the first thing, that the set of natural numbers n is a subset of the set of whole numbers, and whole number is a subset of integer, and integer is a subset of rational number, the set of rational number, and rational numbers are, that is, it is a subset of all the real numbers. You can verify as well. See, the set of natural numbers starts from 1, 2, 3, 4 up to infinity, and whole number starts from 0, that is 0, then 1, 2, 3, like this. So natural number, that means all the elements present in the natural number is present inside the set of whole number, but we cannot tell that whole number is a subset of natural number. Why? Because whole number is containing 0, but natural number is not containing 0. So we cannot say that all the elements of set of W is present in the set N, but we can say all the elements of the set N is present inside the set W. Okay, because whole number starts from 0, then 1, 2, 3, 4, 5, which is the set of natural numbers. Okay, so natural number is containing all the sets except 0. So 0, that means whole number is containing an extra element, that is 0. So natural number is a subset of, that is, whole numbers. Now whole number is also a subset of integer. Why? Because whole number starts from 0 and integer starts from minus infinity to infinity, that means minus 5, minus 4, minus 3, minus 2, minus 1, 0, then 1, 2, 3, 4, 5, like this. So integers are containing 0 as well, 1, 2, 3, 4 up to infinity, and also the negative portions on it as well. But whole numbers are not like that. Whole number starts from 0. So all the elements of whole numbers are present inside this set of integers. So whole number is a subset of I. Then we come that I is a subset of rational numbers. Rational number means also we can say minus 1, minus 2, minus 3, and we can say that the points, that is 2 point, suppose we can say 2.34. This is a rational number, but 2.34 is not an integer. So but 2 is also rational number and also integer. So all the elements of the set of integers is present inside the set of rational numbers. So I is a subset of Q, and also obviously Q is a subset of real numbers. All real numbers means all the numbers, that is from minus infinity to infinity, including the integers, whole numbers, natural numbers, rational numbers, and irrational numbers. So obviously Q bar is also a subset of, okay, that is the set of irrational numbers is also a subset of R. Okay, and another important thing, that subset of phi, subset of phi will be one. Now see, phi, in phi, number of elements, that is cardinal number of phi is 0. So the number of subset of this, we have just written the formula, that is 2 to the power of cardinal number of insect. 2 to the power of cardinal number 10 of phi. So it will be 2 to the power of 0, that is equal to 1. So number of subset of phi is equal to 1. This is equal to 1. That is, the subset of phi is only phi itself. Okay, so subset of phi is only phi. So you can write that subset of phi is phi itself. Okay, nothing is present else that. Okay, and there is no proper subset of phi. Why? Because here you can see that number of subset is 1. So proper subset will be 1. Number of subsets minus 1, that is equal to 0. So no proper subset of phi is present. Or you can say number of proper subset is 0. Okay. So this is all about this types of sets, and we have just done subset, proper subset, and number of subsets, number of proper subsets, and we have done some important things that needs to be remembered. Okay. So today up to this, I think all of you have understood the concepts, the types that we have just learned. Okay. And then we have done the subset, proper subset definition, and then we have done what will be the number of subsets, what will be the number of proper subsets. Okay, we have taken some examples to understand that. And then we have done some important things that needs to be remembered. Okay, so I think you have understood and you can easily able to solve the problems. Okay, so until then, we will meet in the next class. So keep studying hard and preparing well, and prepare well for your upcoming exams. Okay, so all the best. Thank you so much for watching.